And now we finally reach the last piece of material in this chapter, the reactions and preparations of amides and nitriles. Let's start with amides since we've seen a lot of these reactions before in the previous sections. If we want to make an amide, the way we can do this is either efficiently and in a high-yielding manner from acid chlorides and acid anhydrides, or inefficiently and in a low-yielding manner from esters and carboxylic acids. Both of these reactions are pretty similar. From acid chlorides and anhydrides, we can simply add an excess of the amine or the amine and a separate base to get an amide. Esters and carboxylic acids can also be converted directly to amides by a method known as thermal aminolysis. This involves treating the acid or the ester with the amine and a large amount of heat. This is an inefficient method and it only works for very simple amides. In terms of reactions, amides can be hydrolyzed to carboxylic acids either efficiently in the presence of a catalytic amount of acid or inefficiently with a base followed by an acid workup to reprotonate the carbonyl group. Note that this also produces either a free amine or an ammonium ion as a side product of the reaction. We'll focus more on the amine part of this reaction in a later chapter. Nitriles are often considered to be honorary members of the acyl family. The reason why is that they, like the acyl family, have a polarized pi bond, which leads to an electrophilic carbon, and there's two groups that can act as leaving groups. In the case of the carboxylate derivatives, we have a pi bond and a chloride ion or an OH group that can leave. In the case of the nitrile, we have two pi bonds that can leave. Nitriles are less reactive than amides. Let's take a look at the reactions. So the primary reaction of nitriles that we've covered already is their hydrolysis to carboxylic acids. So a nitrile can be hydrolyzed to a carboxylic acid and ammonia, either in the presence of an acid catalyst and heat, or in the presence of a base followed by an acid workup. They also react with strong carbon nucleophiles in a very interesting reaction to produce ketones. Here, benzonitrile will react with methyllithium followed by an acid workup to give acetophenone. How does this reaction work? As we might expect, the strong nucleophile adds to the carbonyl carbon, producing this compound, which you might recognize as an imine ion, the conjugate base of an imine. During the workup step, the imine ion is protonated to an imine, and under these conditions it will hydrolyze itself to a ketone. We can also do an analogous reaction with dibal to reduce the nitrile to an aldehyde. The mechanism is exactly the same. Both amides and nitriles will be reduced to amines with lithium aluminum hydride. Here we have benzamide being reduced with lithium aluminum hydride followed by workup to benzylamine. Nitriles can also be reduced to primary amines with lithium aluminum hydride. I'm mentioning this here for the sake of completeness. We'll discuss this reaction much more in depth in Chapter 22. How do we prepare nitriles? Well, aside from the SN2 route, which we covered earlier, the other way is by dehydration of amides. If we have an amide, we can treat it with a strong dehydrating agent like thionyl chloride. Many other textbooks will list other reagents here like phosphorus oxychloride or other phosphorus halides. These will react with the amide to give us a nitrile, SO2 gas, and two equivalents of HCl. Since this reaction involves the loss of two hydrogens and an oxygen, or H2O, this is why it's known as a dehydration. So to wrap up, how do you organize all this material? These are a tremendous number of different reactions, even though they are all very similar in type and mechanism. The best way to do this, as I always recommend, is by practicing. Where I'm going to recommend you start before we have class discussions on this next week is with a flowchart. So take this flowchart here. Here, top to bottom, this flowchart is organized based on the oxidation state of the central carbon. Note that carboxylic acid has the same oxidation state as the other acyl derivatives, but as it's central to most of these reactions, I've set it aside in order to provide a little bit of clarity to your document. Left to right, this is organized more or less in terms of reactivity. The acid chloride is more reactive than the anhydride, which is more reactive than the ester and the amide and the nitrile, and so on and so forth. Take this diagram and start by trying to connect as many of these groups to each other as you possibly can. Do this from memory at first. This is the important way to practice. You have to do this from memory at first, then check your work with the book in order to see if you've gotten all the connections right. Once you've done that, build on this diagram. What else can you turn amines into? What else can you turn amides into? How else can you use aldehydes or primary alcohols? There's many ways to build on this flowchart to not only practice the individual reactions within the chapter, but also to see where it connects with material from previous chapters. After you've completed this, make sure that you write down a list of questions for class. We'll begin discussing this material on Monday.